Hello everyone. Today I'm going to talk about various centrality measures. We'll be talking about what they are, how to calculate them. We're going to walk through some rudimentary examples, look at some visualizations, and take a look at some real-world applications. But first, let's start off with some definitions so we're both on the same page. Degree centrality is simply the total number of edges that are incident with V. Degree centrality is the most basic measure and can be thought of as the immediate risk of a node for catching whatever is flowing through the network. In degree is a count of the number of ties directed to the node, and out degree is the number of ties that the node directs to others. When ties are associated to some positive aspects such as friendship or collaboration, in degree is often interpreted as a form of popularity and out degree as gregariousness. Closeness centrality is the average length of the shortest path between the node and all other nodes in the graph. Betweenness centrality quantifies the number of times a node acts as a bridge along the shortest path between other nodes. It's worth noting down here that Dr. Sean Everton is a current NPS professor, and he's written a book called Disrupting Dark Networks, and he has a lot of operational experience with networks. Additionally, in italics, we can see some applications of the various measures to social networks. So now let's take a look at some formulas. First, degree and in degree are relatively straightforward, as you can count the number of edges leaving a node as the out degree and the number of edges entering the node as in degree. Summing these two values gives you the total degree. However, closeness and betweenness centralities are not so straightforward. Closeness is calculated as the reciprocal of the sum of the length of the shortest paths between the node and all other nodes in the graph. As a result, the more central a node is, the closer it is to all other nodes. Betweenness is calculated by the following expression, where sigma is the total number of shortest paths from node S to node T, and sigma V is the number of those paths that pass through V. Now we'll run through some calculations on two basic graphs so we can get a feel for what these characteristics are and measures how they translate to a real-world graph. First, I'll start with degree, and as we can see, looking at node B, for example, has degree 1, while node D has degree 4. For in degree, node E has in degree 1, and node F has in degree 4. Node A has out degree 2, while node H also has out degree of 2. Now for closeness, we can see, again, applying the formula of 1 divided by the degree to go to each of the other nodes along the shortest path is 1 divided by that value. So we're going to look at node 6 to start off with. So looking at node 6, to go from node 6 to node 4, the shortest path is 1. Then to go to node 3 is 2, 1, 2. Then to go from node 6 to node 5 is also 2, 1, 2. And the same thing to go to node 2 and node 1 is 3, 1, 2, 3, 1, 2, 3. Now we can standardize this value by dividing the maximum possible value divided by 1. So it's 1 divided by 11 divided by 1 divided by the number of nodes minus 1. So 1 divided by 11 divided by 1 divided by 6 minus 1 equals 0.4545. For betweenness, we're going to look at starting at node 2, we can see how many number of vertices that are not including V by applying n minus 1 times n minus 2 divided by 2. In our case equals 5 times 5 minus 1 divided by 2 is 10. Now we're going to enumerate those pairs of vertices starting at 1, 3, 1, 4, 1, 5, 1, 6, 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, and 5, 6. So we'll start looking at 1, 3. The shortest path to go from 1 to 3 is through 2. So there are there's only one path to go where, and that includes 2. So that number is 1 divided by 1. The next time we'll look at node going from 1 to 4. So we can see the shortest path, there's only one way to go there, and it does not involve 2. So that is a 0. The same thing when we look at going from 1 to 5, there's only one shortest path to go there, and it does not involve 2. So now let's jump over to going from 3 to 5. We can see that there are two shortest paths to go there One that involves 3 to 2 to 5, and then one that involves 3 to 4 to 5. So we can see down here in the denominator that there's two shortest paths to go from 3 to 5, but only one of those contains 2. Therefore, it's 1 over 2. There are additional videos on YouTube, but this one in particular I found to be very helpful as I designed this chunklet, so you should check it out for further research. Now, the following graphics were generated from a software similar to Gephi called Organization Risk Analyzer, or ORA, that was created by Kathleen Carley. The following images depict the various centrality measures on a larger graph. So we can see here, for example, a graph with no centrality measures applied, just for basic understanding. Then we can apply a closeness, and we can see how the graph shifts in terms of who are the important players in terms of closeness. And the same thing here for degree. We can see that Muhammad is the number one as he has the most, has the highest degree centrality. And then we can look at betweenness, and Ali turns out is the informal power broker amongst the network. So now let's take a look at some applications. There are a multitude of applications that necessitate the study of these various centrality measures. As you can see on the slide, I've listed several, but I'm sure you can think of a few more. As an operations researcher, I'm particularly interested in understanding maximum flow problems and shortest path problems. Additionally, the ubiquitous use of social media gives rise to a directed network of followers and following. Lastly, social network analysis provides opportunities for both lethal and non-lethal targeting and understanding the resiliency and robustness of networks. Thank you all for watching.